Equations of fluid dynamics can be derived by calculating moments of the Boltzmann equation for quantities that are conserved. We form moments of the Boltzmann equation by multiplying by a quantity q and integrating it in velocity. So that's the Boltzmann equation here in parentheses, multiplied by q and integrated in velocity. In the following discussion, we're going to assume that q is conserved. Then the moment equation can be transformed into the conservation theorem, as we're going to show. For that, let's split then this equation into the three integrals. Call this equation 1. That's it. Split this into three integrals. And let's treat each of these integrals separately. For the first integral, what we have here is a time derivative. We can use integration by parts and say that the time derivative of the integrand, then applying the product rule, is going to give us these two integrals. The integral that we want is this one here, the first on the right-hand side. So let's isolate it. Okay, now we have the first term here in terms of these two other terms. Let's call this equation 2 and save it. Let's move on to the second integral, the one here on the spatial derivative of the distribution function. So let's play the same game. We have a derivative of one of the terms only, but there are three terms inside the integrand. So if we had the spatial derivative of the three terms, you split them into the product rule. The term that you want is the third one, this one. So let's isolate this, simplifying it already because v and x are independent, because the velocity and the position are independent, the middle integral vanishes. So the term that we want reduces to these two integrals. Again, let's call this equation 3 and save it. Move on to the third integral, which is the one with the velocity derivative of the distribution function. Along the same lines, again, we have only one term inside the velocity derivative. Let's use the velocity derivative on the three terms, apply the product rule. And what we want is only this last term. So let's isolate this. Call it equation 4. Now, if you substitute equations 2, 3, and 4 into equation 1, then we have all of these terms here being equal to 0. And now let's simplify this equation then. So the fifth term here cancels because it is a divergence of a volume integral. So by virtue of Gauss' theorem, we can replace this integral by an area integral and make the radius infinity, where f vanishes. So we remove one of the terms. What other terms can we eliminate? This last term here, considering that the acceleration is independent of the velocity, we can eliminate it too. One last term. Now the second and the fourth term. Now because the quantity q is conserved, the total time derivative of q is the partial time derivative plus the advection term, v partial dx, which is exactly the terms that we see here. So these two terms cancel together. This finally leaves only these three terms. Now let's average. The average value, let's call it angle bracket a, of a quantity a, is the integral of the quantity a weighted by the distribution function. And because the denominator here is a number density, we have that the integral of a quantity a times the distribution function gives you the average of that quantity times the number density. And these are similar to the integrals that we have here. All these integrals are weighted integrals of a quantity by the distribution function. In here you have the q quantity, in here you have q times the velocity, and here you have the derivative of q of the velocity times the acceleration. Then using this definition, then equation 6 becomes this equation below. We substituted this integral here of q times the distribution function by the number density times the average of q. The same thing for the middle term here. We have now a gradient of the average of qv times the number density, and the same thing for the last term. This result is the conservation theorem. For a gas consisting of particles which have no inner structure, there are 5 conserved quantities q. These are the mass, the 3 components of the momentum, and the energy. We're going to use this to find the equations of hydrodynamics.